We're going to start off Chapter 8. It's going to cover potential energy and the different types of potential energy, and then as well as conservation of energy, conservation of all the energies. Okay, so I wanted to start with just some of the equations that we're going to see in this chapter as we go forward. I kind of want to just make a couple comments on each of them. All right, so the first equation we're looking at is this is going to be change in U, and U is going to be our potential energy. And potential energy has multiple forms. The two most common are going to be gravitational potential and the potential due to a spring. And so gravitational potential would just be UG, and a spring potential would be US. And this is just going to be equal to the opposite of work. So the next equation is just taking our equation for work. We said work was equal to the integral of the force times the increment dx. So we just substituted those in there. So that's how we get the second one. This one here is going to be our potential energy due to a spring. Okay. And this is going to be our spring constant. K is our spring constant. X is just going to be the distance, the displacement that the spring is moving back and forth. Change in potential energy is going to be equal to mg times the change in distance. So this is going to be our gravitational potential. All right, and usually, sometimes we see this written as U is equal to mgh, which is mass times gravity times the height. All right, and that's basically the same thing. If you just wanted to find what the potential energy was at a specific point. But if we want to see what the change in potential is, then we would have the delta y, right, the change in height. Okay, the next equation, or the next couple, are actually going to deal with conservation of energy. The first says that our total mechanical energy, which is our kinetic plus our potential, or the change in both of those, is going to be equal to 0. Okay, so this is conservation of mechanical energy. Energy. And the last one is the change in mechanical energy plus the change in thermal energy plus the change in any internal energy is going to equal 0. So this is just really the conservation of all energy. So basically it's just saying that energy cannot be created or destroyed. All right, and then we're going to end the chapter with looking at power. Power is just going to be our change in energy per unit of time. This is going to be power. Okay. So let's get started then. All right, so potential energy. Well, technically, potential energy is energy that can be associated with the configuration or the arrangement of a system of objects that exert forces on one another. All right, so for instance, when you're talking about a spring, which is going to be elastic potential energy, and you have an object on a spring, the distance that the spring moves from its center. So if this is our relaxed point, and maybe we compress the spring so that it moves to here, this distance here is going to be what kind of dictates how much energy it has. Now, if you're talking about gravitational potential energy, then you have, here's the ground here, and you have maybe an object here, and you lower it to here, you're changing the potential energy by this much. Right, so the potential energy really depends on the arrangement or the position of objects. Like we said, there's two most common forms are going to be gravitational and elastic, which is our spring. Okay, so work and potential energy. The change, delta U, remember this is change of potential energy, in gravitational, elastic, whatever, is defined as being equal to the negative work done on the object by the force, gravitational or elastic. So let's look at our figure. A block attached to a spring and initially at rest at x is equal to 0 is set in motion toward the right. All right, so in A we have the object moving. The object moves rightward as indicated by the arrow, right? So the object can be moving in this direction, But since it's going away from its equilibrium position, the force of the spring is pushing back this way, right? And we know that work is FD cosine theta. So this angle between the two vectors is 180 degrees, right? You have one going left, one going right, so the angle between them is 180. So you're going to end up with a negative force, right? Because they're going opposite directions. Now, in B, then the block is moving back towards X is equal to 0. The spring force is going to do positive work, right? So after the force has let go, now the spring is going to be pushing back on the block to the right, and the displacement and the force are in the same direction, right? So the cosine of the angle between them is just going to be 0 because the angle is 0, so the cosine is 1. So you're going to get a positive work. Okay. Conservative and non-conservative forces. All right, so suppose a system of 2 or more objects. All right, so let's just say we have some system, I don't know, like this. A force acts between a particle-like object in the system and the rest of the system. When the system configuration changes, the force does work, called work 1, on the object, transferring energy between the kinetic energy of the object and some other type of energy in the system. All right, so the best way that we can think of this is, let's just think about the Earth and an object above the Earth. All right, this is our first configuration. If we release this object is going to be pulled downward by the force of gravity, and it's going to have a lot of potential energy, gravitational potential energy, when it's up here. As it's falling down, this potential energy is getting transferred into kinetic energy because it's going to start speeding up. Right? So as we're falling down, you get more and more kinetic energy, and you start losing this gravitational potential energy. When you're at the surface, your gravitational potential energy is 0, and your kinetic energy is at its max. All right, so basically, these energies are being transferred from one to the other. This is mechanical energy. So when the configuration change is reversed then, meaning we start pushing the object away, the force reverses the energy transfer and you're doing work W2. Okay. So anyways, in the situation in which the works are opposite, right? So the work due to gravity in this case is going to be positive as it's going down, and it's going to be negative as it's going up, right? Because as it's going down, the force is in the same direction of the displacement, so you're doing positive work. But if you reversed it, you would be doing negative work. All right, this is always going to be true. Work 1 is going to be equal to negative W2. It's always true. And the other type of energy is a potential energy, and the force is said to be a conservative force. So basically what it's saying is a conservative force, you're not really losing any of this energy due to any external factors such as friction or air resistance or anything like that. It's all being conserved in mechanical energy, which is kinetic energy and potential energy. Now, a force is not conservative a force that is not conservative is called a non-conservative force. The kinetic frictional force and drag force are 2 examples of non-conservative forces. When we lose energy to friction or drag, that energy is being transferred into sound, it's being transferred into heat, sometimes even light energy, and we can't really recover that energy in the system. That energy is basically lost. We can't really use it again. All right. So let's look at the path independence of conservative forces. Now, the net work done by a conservative force on a particle moving around any closed path is going to be 0. All right, so a round trip given the total work is going to be 0. So if you start here and you go all the way up to B, and then you come down around this other path and you get back to A, the total work done is going to be 0. I mean, if you think about it, remember our work is equal to F dot D, and these are 2 vectors. The displacement vector would be 0 if you start and end at the same spot, because the displacement is always the position from your starting position to your ending position. So if that's 0, your work is going to be 0. Now, the force is conservative, meaning any choice of path between the points given gives the same amount of work, right? So if I was, let's say I was traveling up a mountain, I could either go straight up the mountain to here, from here to here, or I could take maybe a looping path all the way around and get up to the top. The same amount of work is going to be done because you're doing the same amount of work against gravity in this case. Right? We're working against the potential energy, same amount of work is done. Now, if the work done from A to B along path 1, as shown over here, and the work done from B back to A along path 2, shown here, if the force is conservative, then the net work done during this round trip is going to be 0. So you add the works, both of these together, you get 0, which means your one work is equal to the opposite of the other work. And if the force is conservative, you know we get this. Okay. So let's do a sample problem. All right, the figure shows a 2.0 kilogram block of slippery cheese that slides along a frictionless track from point A to point B. All right, so you have a block of cheese that slides along the track and ends up here. The cheese travels through a total distance of 2 meters along the track and a net vertical distance of 0.8 meters. All right, so along the track, it's taking 2 meters to get here. That'd be really hard to solve because of the curve of the track. We have no idea of the dimensions. But we do know that the vertical distance that it takes is 0.8 meters, right? So going from here straight down to here, oops, a little farther, here to about there is going to be 0.8 meters. Okay. Now, how much work is done on the cheese by the gravitational force during the slide? All right. So first, let's choose this dashed path in the second picture. It consists of 2 straight segments, a horizontal segment, the angle phi, this is just the angle phi, is a constant 90 degrees. Now, even though we do not know the displacement along the horizontal segment, the work done, the horizontal work done, is just going to be given by this. So the horizontal work, oops, do a little h, is equal to mgd, which is our equation for it's force times distance. So we're talking about the gravitational force here, times the cosine of 90 degrees. 90 degrees because the force is down and the displacement is this way. So there's our 90-degree angle. Okay. This is going to be equal to 0 because cosine of 90 is 0. So the horizontal displacement doesn't even matter. It has no impact on the actual total amount of work done by gravity. All right, so along the vertical segment, the displacement d is 0.8 meters, right? And with and both downward, the angle is at a constant 0 degrees, right? Because when you go down, this is our force of gravity, and that's also the displacement, so the angle between them is 0. Thus, our vertical work done along the path, so our vertical work is again mgd cosine of 0 this time, 0 degrees, so that's going to be 1. So you have 2.0 kilograms times 9.8 meters a second squared times our distance, which is 8.0 meters, times 1, which is our cosine of 0. And that gets you about 15.7 joules of work. Okay. Now the total work done on the cheese by the force of gravity as the cheese moves from point A to point B along the dashed path is then going to be, so our total work is just going to be our horizontal work plus our vertical work. So it's 0 plus 15.7 joules. So we get 15.7 joules total. So again, the only component that matters is the vertical component, and this is going to be the total work done as the cheese slides along the track from A to B. All right. Now, determining potential energy values. For the most general case in which the force may vary with position, we may write work as work is equal to the integral of xi to xf. Oops, this is an f. Times our force times the incremental distance. All right, so this is, again, a force that's a function of x times an increment of displacement. You take the integral of that, which sums up all of these little bits of displacement, and you get the total amount of work. Okay, so we know that our work is equal to the negative change in potential energy. So change in potential is delta U. So this is going to be minus from xi to xf. This is basically just saying we're taking the integral from some initial position to some final position. Right, this is going to be the force that's a function of x times dx. Okay. And then simplifying that, we get our change in potential energy is minus our work. So what this is saying is, if I were to push an object up a hill, let's use our hill example again. The change in potential energy from here to here, so the change in gravitational potential, which is mgh in this case, or the change in height, right, is equal to minus work. So it's going to take me so much work to get this object up to the top of the hill, up to the top of the hill, that's also equal to the change in potential energy, right? So, I mean, that's what work is. Work is either giving something energy or taking away energy. Okay. So, gravitational potential energy. So a particle with mass m moving vertically along a y-axis, the positive direction is upward. As the particle moves from y to yf, the gravitational force does work on it. The corresponding change in gravitational potential energy is going to be given as. So let's use our equation for change in potential and come up with an equation that we can use for gravitational potential. All right, so we know that our delta U is equal to minus the integral from xi. Well, we'll use y in this case since we're talking about the y direction. Yi to yf times our force, which is in this case just minus mg. That's our gravitational force, right? It's pulling down, and times dy. Now we have the negative in there because it's pulling down. The gravitational force is in the downward direction. Okay, this is equal to simplifying this, getting rid of the negative signs and pulling out mg because it's a constant. We can pull that out of the integral. So now we just have yi to yf times dy. Now the integral of just dy is simply y. Right? Basically it's the integral of a constant. So you have a constant. When you take the integral of it, you just get whatever the variable is. Alright, so this is going to be mg times y. And the limits here are from yi to yf. Oops. To evaluate this, we take the top minus the bottom, and we plug it into our variable here. All right, so we have yf minus yi. So that would be, so our change potential is then going to be mg, which is our constants out front, and then we have yf minus yi. And this is simply mg delta y. Right, our change in potential energy. Delta y is our change in vertical displacement. All right, so again, our simple equation for our change in potential energy, gravitational potential energy, is mg delta y. And like I said, if you wanted to find just what the potential energy was, you would use potential energy. Gravitational is just mgh. right, or mgy. All right, the gravitational potential energy associated with this particle Earth system depends only on the vertical position y of the particle relative to the reference position y is equal to 0, not on the horizontal position. All right, so again, the only thing that matters when we're talking about gravitational potential is our y displacement. All right, so let's talk about elastic potential then. So in this block spring system, right, we have, something like this, a spring. The block is going to be moving on the end of the spring with a spring constant of k. As the block moves from point xi to xf, the spring force, right, this is our spring force, we saw this last chapter, force due to spring, does work on the block. And now the corresponding change in elastic potential energy would then be given by. All right, so we're going to do the same thing. We're going to derive an equation for our potential energy due to a spring. So delta U, and I'm just going to put a little s there so we know that it's a spring, is equal to minus xi to xf, because that's how the block's moving from xi to xf, minus kx dx. Right, this is our force times our displacement. We can pull out the k because that's a constant, and these negative signs are going to cancel out. So we have k times the integral of xi to xf times x dx equal to, this is just going to be equal to 1/2 k x squared, and it's going to be the limits xf to xi. Alright, so how do we do the integral? So you just have the integral of a variable. When you do the integral, you always take the exponent, you increase it by 1, and then you divide by that number. Alright, so for instance, this is x to the 1. So I increased x to the 1 to x to the 2, so you add 1 to the exponent, and then you divide by 2, right, because that's the number that we raised it to. And I pulled that 1/2 out front, right, because that's a constant. Alright, so now we just see that our delta U for a spring is going to be 1/2 kxf squared minus 1/2 kx I squared. And again, we take our xf, we plug it in, so we had xf squared, and then subtract that from if you had the xi in there. So put in the xi, you get xi squared, right? And I just simplified that and separated them. All right, so in the reference configuration in which the spring is at a relaxed length and the block is at xi, which is equal to 0, right? So if this value here is just 0, then our potential energy due to a spring is going to be given by 1/2 kx squared, where x here is going to be the displacement away from whatever that center point is. Alright, so let's do one last example. Alright, a 2.0 kilogram sloth hangs 5 meters above the ground. Alright, so here's our sloth. He's 5 meters above the ground. What is the gravitational potential energy of the sloth Earth system if we take the reference point y is equal to 0 to be 1 at the ground, 2 at the balcony floor, that is 3 meters above the ground, 3 at the limb, 4 1 meter above the limb. Take the gravitational potential energy to be 0 at y is equal to 0. Alright, so kind of what this picture is showing is in our first condition, we're saying that the ground is going to be our reference point. The ground is going to be where gravitational potential is equal to 0. Alright, so 5 meters above that is where our sloth is. In the second case, we're taking this balcony to be 0. All right, and gravitational or potential energy in general is all based off some relative point, and you can pick whatever is convenient to have as a reference point. So we can choose the balcony to be a reference point, or we can choose this limb to be a reference point. We can say this is where gravitational potential is 0, right? Or we can choose a meter above that to show where gravitational potential is 0. All right, so let's kind of work through these. So it's asking for what the gravitational potential energy is at each of these positions, or each of these conditions, I should say. All right, so we know that gravitational potential, and I'll say this is 1, is equal to mgy, which is going to be 2.0 kilograms times 9.8 meters a second squared, times our y, which is 5.0 meters in this case. So this is going to be equal to 98 joules. All right, that's when so it's 5 meters because I'm saying that our ground is our reference point. Now in the second condition, we're using our balcony as our reference point. So potential energy is mgy. So that's just going to be mg times 2.0 meters this time, right? Because we're going from the balcony up to here, which is now 2 meters. That's going to be equal to 39 joules. Okay. 3, potential energy is mgy. So now we're saying our limb is our reference point, so our limb is our 0 position for the distance. So this is going to be mg times 0 meters, so that's just going to be 0 joules, of course. And then for our fourth condition, it's going to be 1 meter above, so it's mg, and now we have a negative 1.0 meters. So we're going to have a negative potential energy, negative 19.6. Okay, well this is just potential energy, right? I mean, it's based off some reference point. In the second part, it says the sloth drops to the ground. For each choice of references, what is this change in potential of the sloth Earth system? All right, so for all 4 situations, we have the same delta y, the same change in position, right? Because you're going from here to here. In this case, it's going to be 5, or 0 minus 5, so that'd be negative 5. From here, it's going to be negative 3 minus 2, that's negative 5. For here, it's negative 5 minus 0, again, negative 5. Right? In this last condition, it's negative 6 minus negative 1. So that's also negative 5. All right, so our change in y in each case is just going to be negative 5. All right, change in y is negative 5 meters. So our change in potential is going to be mg delta y. So that's just going to be 2.0 kilograms times 9.8 meters a second squared times negative 5.0 meters. So our change of potential is negative 98 joules. So we can see that really a potential energy by itself is not very, it doesn't give us much information, right? But if we saw a change in potential, that really tells us a lot more about the system, right? In each case, the change in potential is going to be negative 98 joules. All right, that's it for this lecture. We'll pick it up next time.